Hello friends, in my previous video I have discussed in detail about the physical structure of Mosfet and the device operation, and from that concept you know that this is the basic cross sectional view or side view of a Mosfet, where there is a p-type substrate is there, and in the p-type substrate there are two regions where there is high doping concentration of n-type semiconductor. So this is denoted by n plus, that is high doping concentration of pentavalent atoms are there or elements are there. So what we do here, there is insulator layer in between gate metal layer and the body or p-type substrate, and in the conductive plate or in the metal layer of the gate, for this figure we are applying what, that is positive gate potential. Okay, and you know as a result if we keep on increasing the Vg or this positive potential from 0 to higher values, initially what will happen, initially there will be formation of depletion region, and then after that free electrons will accumulate just below this insulator layer and will form a channel in between source and drain. And then if we apply positive potential in the drain, what will happen, the electrons from the source will flow through the channel which is formed in between source and drain in this p-type substrate just below the insulator layer, and the free electrons will reach in the drain side. And you know that current flows in the opposite direction of flow of electron. So as electrons are flowing from source to drain, so current will flow from drain to source, so that I have denoted the current direction like this. Okay, so this is the basic device structure and operation of the Mosfet, and this is we are considering NMOS. Why? Because the free electrons are forming the channel in between source and drain. So N channel Mosfet, because electrons are negatively charged, so this is called N channel Mosfet or N Mosfet. Okay, or NMOS. Okay, or NMOS transistors, whatever you say. So now you just consider, if you observe carefully this structure, you can find we are applying two potential. One is Vg and another one is Vd, that is drain potential, another one is gate potential, and here current is flowing from drain to source. Okay, so this current, how this current which is flowing from drain to source are dependent on the gate potential and drain potential, that's what I am going to discuss. So for this Mosfet current, obviously it is clear there are two characteristics will be there. One is ID, that is drain current, versus Vg or applied positive gate potential graph, keeping the drain potential Vd constant. That is nothing but this current versus this voltage graph, keeping this voltage as constant. And another graph can be ID versus Vd graph, keeping Vg constant, that is this current versus this voltage graph, keeping this gate voltage constant. Okay, so these are the two possible characteristics of Mosfet. Okay, you can define for a particular device. Now let us try with ID versus Vd graph, which is comparatively easier. Okay, that is drain current, that is nothing but this drain current versus applied drain potential, keeping the gate potential constant. Okay, how the graph will be there, let us try to understand. So ID versus Vd, keeping Vg constant. So just consider the hypothetical semiconductor device which I have encountered when I was discussing the basic device operation of Mosfet. Just have a quick recap. In the above, here there is conducting plate, then there is insulator, and then there is p-type silicon is there. Okay, and here in the conductive plate, in the vertical direction, in the conductive plate and just below the p-type silicon, we are applying V1 potential, where positive terminal of the battery is connected with the conductive plate, and in the left to right direction, if you consider, what will happen, that here we are providing V2 potential. And you can easily understand that if we apply positive potential in this as V1, so what will happen, that the conductive plate will become positively charged and it will attract the electrons or minority electrons which are present in the p-type silicon, okay, and the minority electrons will slowly form a channel of electrons just below the insulator, right? So basically nothing but V1 is acting like a gate potential in the MOSFET, right? That is Vg, and if channel is formed from left to right, there will be no current flow because we are not applying any potential. So what we will do, we are applying a V2 potential in from left to right. See, the positive potential of the V2 potential battery is connected to the right. So what will happen, the electrons will be attracted from left to right. As a result, current will flow from right to left. So the V2 potential is the reason for the current flow through the channel. So that basically we can say comparatively this is V2 potential which is acting like a applied drain potential or VD, right? Now our intention is how the current which is flowing from right to left will vary if we change V2 keeping V1 constant. So first thing first, if we are keeping V1 constant, so there will be not much hamper in channel of the electrons, but what will happen, see, current is flowing, we are applying potential, so obviously the current will flow follow the Ohm's law, that is V is equal to IR. So nothing but if V increases, the current flowing through the channel will increase. Basically the channel is acting like a resistor, right? Because we are applying voltage, we are getting current, and simple, there is no non-linear expressions will encounter here. So basically in simple words we can say V is equal to IR is going to follow. So if this potential V2 increases, or in terms of MOSFET if we say if VD increases keeping VG constant, then simply V is equal to IR going to be followed, that is I will linearly increase with applied drain potential. So as a result, what will be the graph? That is simply this one, that is for constant V1 or constant V1 for this hypothetical semiconductor device, or constant VG or gate potential for NMOS, what we will get? We will get the drain current versus applied drain potential graph like this one, that is linear graph. Why? Because it will follow Ohm's law. The channel will behave simply like a resistor, nothing else, right? Now another characteristic is nothing but ID versus VG graph when drain potential is constant. And how that will be? See, if we, so in that scenario what will happen, just consider this hypothetical semiconductor device, we are making the VD or drain potential constant, that is V2 is constant, but we are increasing V1 or gate potential for the MOSFET. So obviously it is clear from the device operation of MOSFET that if we increase V1, the thickness of the channel will increase. Basically accumulation of free electrons just below the insulator layer in the p-type silicon will increase. As a result, the channel will become thicker and thicker. That means the area of the channel will become more and more if we increase the V1 potential, or in terms of MOSFET if we increase gate potential. So see, as I told you, the channel is behaving like simply a resistor, right? And now if we are increasing V1, the area is increasing because the thickness is increasing. You can say, or you can intuitively understand like this, that is the accumulation of electrons just below the insulator will be more. So as a result, the area of the channel will become more. And how the resistance dependent on area, just have a recap. See here I have written the same thing, that is ID versus VG keeping VD constant. So that graph we have to consider like this. So if VG increases, the thickness of the channel or the accumulation of electron just below the insulator layer in the p-type silicon will increase. That will increase the overall area of the resistor. That is what, if VG increases, thickness of the channel increases, that is in terms of area it will increase. And you know from the basic concept of physics, there is R is equal to rho L by A. So if A increases, R will decrease. And if you consider our rho and L are not varying, right? Length of the channel we are not varying and rho is constant. So R proportional to 1 by A, that is Y proportional to 1 by X, nothing but simply rectangular hyperbola type graph. So with respect to change in area, resistance will vary like rectangular hyperbola, and here resistance is decreasing like rectangular hyperbola. So simply, obviously, we can say from the basic mathematical graph concept that ID will increase like parabolic, that is like this type of figure with respect to increase in VD. So as VD increases, area increases, resistance decreases like this type of exponential or rectangular hyperbola graph. So ID versus VD graph will be like increasing exponential or rectangular hyperbola graph. Okay, this is not rectangular hyperbola, like increasing parabola graph you can say. So basically that's what ID versus VD graph. But tell me, from the device operation concept, you just think whether the graph is correct. As soon as the VD, or sorry, here I have done mistake. This is not VD, this will be VG. Okay, that is gate potential, not VD. Sorry, the VD, the graph will be this one, ID versus VD. This will be VG. Sorry for this mistake. This is gate potential versus drain current versus variation in gate potential graph. So this will be VD. So sorry, VG. Okay. So see here I have written here correct, that is VG, but mistaken here. So you just consider this as gate potential or VG. Sorry for this mistake. So see, ID versus VG graph is looking like this. But tell me whether just if you increase the gate potential just above 0 volt, whether you will get drain current? No, the channel is not directly formed as soon as the gate potential goes beyond the 0 volt or increases in the positive direction beyond 0 volt. First, channel has to be formed, and you know, to form a channel, certain amount of minimum amount of gate voltage has to be provided, so that voltage is called thermal voltage or VT, sorry, threshold voltage or VTH, which is required minimum amount to form at least the channel. And if channel is formed, then after channel formation only there is possibility of current flow in between source and drain, right? So what will happen? This graph is wrong. The actual graph will be just little bit modified version of this graph, and that is this one. See what is happening? If the applied gate potential, here also it will be VG or gate potential. If the gate potential is less than the threshold voltage of the Mosfet or VTH, no current will flow, that is ID or drain current is 0. And as soon as the gate voltage goes above the threshold voltage, it will follow this graph. Okay, that is it will increase rapidly. Okay, why? As you know, that is R will decrease rapidly, so that current will increase rapidly, but everything will happen beyond the threshold voltage. That's what the important point, because to form the channel, minimum amount of gate voltage has to be provided, which is equal to VTH, and if the gate voltage is lesser than the threshold voltage, no current will flow from source to drain or drain to source, whatever you consider for PMOS or NMOS. Okay, so this is the gate voltage, that is drain current variation with respect to applied gate potential, keeping the drain potential constant. Here I have done mistake, no need to confuse. Here this will be VG or gate potential. Okay, and this graph, that is simply V is equal to IR, Ohm's law graph for the drain current versus the applied drain potential, keeping the gate potential constant. Okay, so these two characteristics are very important. If you have lab in the VLSI, obviously in most of the universities in India there are VLSI labs, obviously in other countries also. So see, from this graph you can do an experiment, that is suppose VTH or threshold voltage for Mosfet is unknown to you. So how you can determine the threshold voltage? Simple. First you make one circuit, okay, where you take one NMOS, you provide gate to source potential, gate to drain to source potential properly, and then you just try to plot the drain current versus applied gate potential graph, and you just observe that for up to which value of gate voltage the drain current is 0 or very minimum. You will not get exactly 0, but you will get very lesser value, and that voltage up to and after that voltage the current will increase rapidly. So that voltage will be nothing but the threshold voltage of that NMOS. Okay, so in this way you can do such kind of experiments, and this will become very interesting when you will visualize the theoretical concept in your laboratory experiments. Okay, because visualization will clear your concepts. This is all for my this video. If you have any doubt, you can ask in the comment section. Thank you for watching.